Hello everyone, welcome to 𝐿ustraca. So in this lecture we are going to see how RCDC is estimating the boundary element forces of a RCC shear wall. So let us you can say get started. So here I have an analysis model which I have taken from 𝐀𝐧𝐝𝐫𝐾 you can say analysis model, and I have already performed the design of the columns and the shear walls in the RCDC. So to know more about the design procedure and you can say how to import the forces and all, you can join my detailed you can say course on RCDC. The description of the course you will find in my in the description of this lecture. Okay, so just check the description of this video and you will get all the details regarding the course. So now let us jump into the today's problem. For today's problem we will be selecting this particular wall, which is PW7. Okay, so as the design is already performed, I will go to reports and I'll go to this you can say design calculations. So let us select this PW7 and click on OK. All the nomenclatures are given, all the other procedures are given. I will just directly go to the place where the RCDC is estimating the boundary element force. So you can see here the RCDC is finding the maximum compressive force in B, which is the boundary element. So generally what we do, if suppose we have a you can say shear wall, okay, or structural wall, first for this in plane moment, what we do, we find out the stresses, right? So how we'll be finding out the stresses? This is not only having a moment. Suppose this is my mu. It is also having some axial load pu. Okay, so I will not write pu, it is not ultimate. I will write p, I will write m. Okay, so what we can, how we can find out the stress? The stress will be finding out by P by A plus minus M by Z, correct? So for P by A we will be getting some you can say distributed forces or stresses. Then for M by Z it may be we may get some tension also, so we may get a like this. So here it is tension, here it is compression, right? Okay, so then if we add these two, so the distribution will be something like this. If we add these two, then what will happen? If the axial load is very high, then we may get a trapezoidal shape of stress distribution along the length of the wall, or if the this p value is not that much high, we may get some tension also at this direction. So it may be like this. So we are getting some amount of tension here and some and compression in the other side, correct? So this is the stress distribution. So what we do, that if this stress, this compressive stress is greater than 0.2 FCK as per IS 13920, then we assume that we need to provide you can say boundary element. Okay, now what we do generally, we assume a length of the boundary element. Suppose we have assumed some length of the boundary element A in both direction. Okay, then we have left with the middle length, which is actually called web. So if the total length is L, so it is L minus 2A. This is the total middle length, which is my web, and this is suppose the thickness T. So what we do, we find out the moment capacity when we are doing it manually as per IS 13920 methodology. So we find out the moment capacity of this particular web. So suppose moment capacity is m web, and we also find out the axial capacity of this web, which is my p web. So once we got the m wave and p wave, or what we can do, first we find out the moment capacity, and whatever p we are getting from area I can say proportioning, we can find that how much p this particular wave area will be taking. So it is my p wave, actually not the capacity, we find out from the area proportioning. Okay, so we got the m wave and p wave. That means this is the amount of force that this wave part will be taking. Then what we do, we have the actual pu, so we deduct the p wave from the pu and we deduct the m wave from the mu. So this force, this resultant force, I mean suppose pu minus p wave, we are getting p boundary element and m boundary element. Okay, so this p boundary element, actually p taken by the two boundary elements, so we do p by 2, so we will be getting force axial load here, which is p boundary element by 2, here also p boundary element by 2. This is the compressive load, right, force. And then this moment we convert into a tension compression couple. How? We have this lever arm, the center to center distance between the boundary elements assumed with the assumed length. So suppose this is my lever arm, so this MBE divided by lever arm, if we do, so if the direction is this, so it will be, here we getting some tension, here we getting some compression. Okay, so here this is the compression force, plus we have the compression due to this axial load, and here we have tension force minus you can say, sorry, the compression due to the axial load minus the tension, so you get some force here, right? So this is how we can find out the, you can say, force in the boundary elements. But RCDC has a different approach. RCDC has a different approach. So suppose I have a net stress distribution like this over the length of the boundary element. Okay, so this is my positive stress, this is my negative stress, I mean this is tension and this is in compression. I'm talking about the net stress distribution. Okay, and if I draw the you can say wall, so suppose the wall is something like this. Wall is something like this. Now generally we can assume the boundary element length initially and we can check, but RCDC has a different approach. How it is doing? So it is following some you can say international papers and the examples given in different publications of IIT Kanpur. So how it is doing? It says that if the moment the axial capacity of the section, so axial capacity they are finding, suppose P0 equal to 0.8 times, they are finding like this, 0.85 FCK, okay, AC plus Fy into AST. Okay, so this is how they are finding out the axial capacity of the section. So this says if the analysis PU, okay, if the analysis PU is less than 0.15 times this P0, then BE length will be it will be 0.15 times LW. LW is nothing but this length. I will just write it here. This is my LW. So 1.15 times you can say LW. This is the first case. Second case, they are saying if PU is greater than 0.35 times P0, then BE length will be, sorry, I'm writing over this actually, just please do understand. So it will be 0.25 times LW. And if the third case is if the PU is in between this 0.15 P0 to 0.35 P0, in this case the boundary length should be within the 0.15 LW to 0.25 LW. You can do the linear interpolation depending on the value that you are getting. Okay, so based on this you will be getting some, they are getting some length actually. Okay, boundary element length, correct? Now where we are finding the force? We are finding the force somewhere here at the center, correct? So let us draw a line here. Let us draw a line here. So here is the line I have drawn in the stress diagram. Okay, so first of all, to find out this slope, that means the change of stress along the length of the wall, how we can find out this you can say change of stress along the length. So if you find out, suppose this is my positive stress, okay, so I can say this is my SC compressive stress, this is my ST. Okay, so if I do SC minus ST, as I am considering that SC is greater, SC minus ST, so I am getting change in stress. And if I want to find out what is the change in stress per meter length, then I need to just divide this by LW. So this, suppose I am considering S1. So this is nothing but change in stress per unit length, which is also called as slope of stress. Okay, slope of stress, understood? So you can see here, just let me just turn it off. You can see here RCDC is first finding out this slope of stress. Let me just delete this and write it here. You can see RCDC is first find out this slope of stress. Okay, so now after finding out the slope of stress, then what we can do? Let me just undo this and get it back here. So after finding out this slope, that what we can do? So now we know what is the rate of change of stress along the length per meter unit, per unit length, right? So now I want to find out you can say force here. So if this is, suppose I am just omitting this. So I suppose this is my A, this is my B. Okay, so I know what is the stress here, which is, it is A is equal to P by A plus M by Z, correct? This is A. So now if I want to find out the stress at this particular location, how I will be finding out? Obviously here the stress will be reducing from this particular edge, and we know what is the rate of change of stress. So if we just go this direction, that means the stress will be reducing. So I'll do minus, it is reducing. How much? So I know the rate of change of stress is nothing but S1, which I found out the slope. So if I write, this is slope rate of change of stress, right? Or we can say a change of stress per unit length. Now what is the exact stress value here? How we will be finding out? So I got the rate of change into the length, which up to what length I want to go. So it is, this is, if my total boundary element length, suppose A, so I'll be going up to A by 2. So into A by 2 will be giving me stress at this particular location. Okay, so if you see the first case, what it is done, they have given P by A plus M by Z P by A plus M by Z minus slope into boundary length by 2. So they got the stress at this particular location. In the second case, now here I am considering this B is a tension. It can be compression also. Okay, there is no problem. So here B is nothing but P by A minus M by Z, correct? Now I want to get the stress at this particular location. Now this P here, it is negative, and I am coming this direction. So I know it will be reducing, but it doesn't mean I need to go, you can say I need to, as it is reducing, I need to make it negative. Why I have got given negative? Because of the direction. It is in the opposite direction of the axis, so it is negative. It is coming this direction, so it will be positive. So minus and plus, so obviously automatically it will be reducing. Okay, so in case if you have a trapezoidal shape, so this is plus, this is also plus. So obviously if this direction it is coming plus, then it will be more, so naturally you will get more. Here we want to reduce it, so even if we doing plus, but this value is negative, so automatically it will be reducing. So generally this is what we are doing. I mean, what RCDC is doing, what it is doing, it is finding out the stress at the center. So now how it will be? It will be this direction, so we'll go positive, so plus same S1 into A by 2, because S1 is the slope change of rate of change of stress multiplied by how much length? A by 2. This is A by 2. I know if this is A, this is A by 2. So what I got the stress in both the direction. Maybe it is the tensile stress and the boundary element at this particular site when the moment is in along this direction. Okay, I'm talking about moment. The other direction, the same opposite will be happening. So we found the stress at the boundary element. Okay, so now we need to find out the force. So it is very easy. Now you can see, if I just delete this and I write this, so we found the compressive stress, we found the tensile stress. So let us talk about the compressive stress, because for this calculation, for this load combination, the compressive stress is higher. In the other combination, you will see the tensile stress will be higher compared to the tensile stress. If you see, in this case it is 9.49 49, in the other case it is 8.2. so here the tensile is governing, here the compression is governing. So now if you understand one, the other one is the same. So now how to find out the compressive force on the boundary element on this direction? Like here I am getting some compressive force. So how to find out the force? I know the stress value. Okay, so here I am getting suppose 13.59 stress. So 13.59 multiplied by, now this boundary element length, what RCDC is assumed based on the methodology that I have just explained a bit minute ago. So you can see, just go down, you will see that boundary element is considered, the length of the boundary element is 300 mm and this thickness of the wall is 200 mm. So if I just go to this place, so I know 13.59. So 13.59, it is in Newton per mm square, multiplied by 300 is the boundary element length. Here this formula has a problem. Boundary element length into thickness will be also there. So into thickness is 200 mm. I'll get the force. So if you just calculate 13.59 multiplied by 300 multiplied by 200. So you can see you are getting a value of 815,400 Newton. If you divide it by 1000, you will get 815.4 kilonewton. Now here I think the value of is around 815.29. we are getting a bit higher. Maybe they have taken effective depth instead of total, total length of the boundary element. They may be taken the effective length, so that is a different thing, but we are getting this 815. If you see, we are getting a similar value here. Okay, so this is how they found out the compression. The same way they will be finding out the tension also, the tensile stress multiplied by the area, so there will be tensile force. Okay, so this is how the boundary element forces are being calculated in RCDC, which is it's not the same way that we are finding for the in the manual calculation. Okay, so you can use this methodology also in the manual calculation to find out the design, you can say, force for the boundary elements. Okay, so I hope it is clear to all of you. To know more about the shear wall design, how to design it manually, or how RCDC is doing the complete design, so I have explained it in detail in my RCDC course, so you just have a look on it, and I'll be making more such videos in my YouTube channel also. So if you are not a subscriber, do subscribe, and if you are already a subscriber, please stay tuned, and we'll be you can say posting more videos in the coming days. Thank you, and see you in the next lecture.